Okay, well, thank you again for having me. I'm excited about this presentation because it's a culmination of, honestly, the last two presentations we did. In the seventh webinar, the global webinar, we introduced the McGinty equation, kind of explaining the combination of quantum field theory, fractal geometry, and gravity is what that equation does. In the eighth conference, we spoke about how that equation can be used to mitigate quantum computing errors and in error correction. And that was really one of my and our main focus at that time, was because in doing that, it really opens up many possibilities with quantum computing. So what we have is we've moved forward from there, and the next logical place where we were really looking to make a major impact was in hydrogen, and specifically hydrogen splitting. It's kind of been a holy grail for many years, the idea of being able to take water, split the hydrogen out, use that to push the pistons in the car, and then exhaust pure oxygen. We've figured out a way to do this and have been working quite extensively on it. So that's what I'm going to be sharing today. So let's get started here. We're calling it quantum enhanced hydrogen splitting. And what we're going to be speaking about is using the MEQ-based technology. So using the technologies and algorithms, there's about 28 different algorithms that are involved with this that are all based off of the MEQ framework. So and I'll go through those. So the reason why we're focusing on this area is we all know that, global warming is something that's happening. It's measurable. We've noted it for a long time. I'm actually in Minnesota in the United States. It's early March. There's usually several feet of snow on the ground here. There's none. That could be an anomaly. However, there's so many different things going on in the world right now that I can't help but think that it's somehow connected. These are some stats that we kind of looked at just in general, why to focus on hydrogen specifically. Right now we're still using 80% of fossil fuels for our energy, for our electricity, which is not sustainable, and it has to change rapidly if we're going to meet some of the climate goals that we've been kind of tasked with as a society. Hydrogen is unique in that it's a very clean fuel and it can be stored. There's some very unique method or ways we can do this when we can do this at scale and efficiently. Those are the two things that we're really focusing on here. And there is going to be more new tech that comes out as AI continues to evolve and develop that we'll also be able to integrate in with this as well. So really, that's kind of what we're trying to focus on, is how can we do this and make a difference? Kind of the so what. Okay, so what? There's an equation that we don't know about. What does it do? So we've developed what an MVP is a term called minimum viable product, which means that it works. It may not be the stream of the line, but it works, and it meets what we need to do. So that's what our goal has been, is we want to make a hydrogen splitting semiconductor and then move that into actually making hydrogen splitting spark plugs. And these spark plugs would fit into any vehicle primarily, and could then transition us over to water from fuel. That's kind of the overall dream. There's going to be a lot more that goes into that, and we'll kind of explain that. So what the impact, how we're going to measure that impact, there's a number of different ways that we're taking a look at it. But we're actually, we want to look at the carbon emission reduction, the greenhouse gas reductions. We want to look at different ways that we can use hydrogen splitting semiconductors for different fuel cells to really, I guess, there's so many things we can do with the hydrogen fuel cells to really boost up other forms of renewable energy as well too. So the approach is, we want to take a very good close look at the material selection and also really scrutinize the theory behind it. And we've been doing that along the way, and it's been turning out pretty well. So this is kind of the timeline that we've been working with. The fractal correction term was devised or developed last year. We validated that again last fall, moving into this stage that we're in now, which is the developing of the prototype. We're expecting or hoping to have this done by the beginning of 2026, so that we can actually be testing them in internal combustion engines. And why it's valuable, why do this? It may seem obvious, but I'm going to kind of spell it out here. If we can have an efficient, renewable source of hydrogen energy, it will change the power grid landscape entirely. It will change the way we do remote energy and power, beyond things such as our spark plugs for cars. It will transform feedstock industries. Think of ammonia and methane and things that are hydrogenized. All of those things can now be made with clean, renewable hydrogen. So this brings us to, so how will this change things? It actually has a transformative effect on the entire global economy. If we're able to accomplish this, and we're well along our way there, it will literally unlock new billion-dollar markets in hydrogen energy and potential, which will benefit all people involved and the planet. So this is just a little note to kind of say, you know, what we do today has a direct impact on what will happen tomorrow, and from a man that we all know well. So this is an example of what we're doing today. This is a prototype or a vision of what a high pressure alkaline electrolysis system would look like, which is that technology has been around for quite some time. However, if you're familiar with it, it's energy intensive and very, very large pieces of equipment and those types of things. So we looked at that first. We wanted to find ways that we could reduce the energy use and primarily increase the hydrogen output. So if we can get more hydrogen out of it over time, obviously that's going to make an impact to costs. So we want to improve the efficiency and then decrease in production costs. So really the main focus here is to increase that hydrogen output. So in our conversations, where we kind of taken this to is we're looking at reducing the overall power consumption of electrolysis from about 30 to 38 kilowatts down to 15 to 18, which will make a dramatic increase in that amount, the production we can do for the energy that's consumed. So to do this, what we're going to do is we're going to use new electrolyte surfaces. This is an example of one. These are complex patterns that are utilizing fractal geometries. We use the MEQ equation or framework to determine what these electrolyte surfaces should look like, so that they're dealing with some of the subtle perturbations of gravity. This kind of shows the efficiency in some of the simulations and the tests that we've been looking at using this new material versus the old, and then the durability, of course. We're seeing that to be a little bit higher as well too. But again, these are all in the simulations for the prototypes. The design optimization, that was kind of what I showed you, some of the smaller systems that are a little bit more efficient in general, but we want to model the original, we want to simulate performance, and then we're implementing right now the design improvements, and next stages will be to do the validation. One of the really nice thing about this is that it does integrate in with other renewable energies, so like solar power and wind power, in concert or in combination. We feel this is going to be a key to reducing any problems with the power grids. By utilizing the hydrogen energy, the hydrogen power to power the solar and wind as well, that's another way too that we can continue the sustainability efforts. which brings me to sustainability. And this is kind of where we're at right now, is we're at number one in this, where we're optimizing the hydrogen production efficiency. Because right now, the way that we're doing it is using the best science that we have. However, we've got some new science and new tools in the form of advanced artificial intelligence that's really showing us some pretty neat things. So these are kind of the steps down to where we're going to get to the point where I'm saying using the actual solar and wind power to actually power the hydrogen production as well. So what is hydrogen splitting? And so how do we get to that point? Because just generating hydrogen power is much different than hydrogen splitting. So what we're going to do is we're building semiconductors at the nanoscale that will be able to split the water and hydrogen and oxygen. That has a great potential to affect everything from our phones to our wearable devices to all kinds of different nanoscale type of technology, along with much larger things up to and including ships and boats and all kinds of things. So, and we'll talk about that. So the way hydrogen splitting works is we're basically using electricity to split the water molecule. It will then split into hydrogen and oxygen, and the hydrogen is used for the power, and that would then push the pistons or generate the fuel cells, whatever we need to do for the electric ones, and then would then exhaust oxygen. The idea would be is that for the given car, like a car example, it would run on solar power during the day because there would be semiconductors that can just take solar power and would charge it up. But if there's no sun or no solar power at all, it could run on water. And that would then be an amazing mark forward. How the McGinty equation works in this is that we have the ability to utilize fractal geometry to really determine what they call the perturbations of the gravitational force in the quantum field. What that allows us to do is to really zero in and with a very finely tuned eye or lens, look at quantum tunneling. We have algorithms for band gap engineering, and we also, we look for passive defects as well too, so that we can, mix the best of all these three different ways of going about it. And then this is a little more close up of how we actually are going in, and these are fractal designs based on fractal geometry and the way gravity would affect and change things. So this is a little bit more about what we call like quantum enhanced defect engineering, and this is kind of one of the grids that goes along with the algorithms. But basically what it's showing here is it'll show how the defect density would kind of show us how it affects the different, the efficiency of the actual splitting itself. But we have a number of different ways to kind of go about this, and this is one of the algorithms that we're using. We're also using the doping optimization. Really the key here is that we're really extending that range, and we're able to do that through the equation. These are some of the other areas too where we're seeing that in doing this process, we get much better enhancement of the mobility, and also the quantum coherence is quite a bit better as well. And this is kind of one of the other algorithms that what we were working on that kind of spawned some of these other ones. This was the quantum chaos analysis. That was developed again at the beginning of last year as part of this process. We validated the model last year. We're wanting to integrate the model into the reaction pathway simulator. We started working on that, and now we're doing simulations. So hopefully we'll be publishing some more work on this towards the middle of the year. Since we've begun doing these presentations, we've actually published 5 pieces in the International Journal of Theoretical and Computational Physics. that have all been double-blind reviewed. So that's been helpful at getting the information out to academics and to people that can use it. So some of the takeaways here is that by using the McGinty equation framework and utilizing quantum field theory, fractal geometry, and gravitational influences, we can now map some of the different reaction coordinates. And by mapping these reaction coordinates in the tunneling pathways, we'll be able to better understand it. And that's the first step in actually creating a final working prototype. So some of the applications that we can use it for, again, the semiconductors can be used for solar panels, where the simulations are saying that we're like going to be able to double the efficiency of solar cells. With wind turbines too, we can optimize the blade designs. There's other different things that go into that. There's a whole, I have a whole paper on that one. Lithium-ion batteries, we're seeing a 10% increase in energy density. I spoke earlier about the smart grid and how that we can use stored hydrogen to when there's disasters, when there's other types of things, in order to regulate and smooth out any of the dips and valleys in the power grid. And then hydrogen fuel production, again, is that's the big one that we're talking about today. This was kind of a funny thought, I thought. This was Sheikh Yamani was an OPEC oil minister, and he had, this is a quote from him, but I thought it was pretty relevant considering what's going on with artificial intelligence and the major I guess jumps in knowledge that we're seeing over even the past year or two. So how we're getting to this is in order to make this jump from the hypothetical Stone Age into a real working hydrogen powered economy per se. These are the kind of the ideas behind it. So the theory behind it is to utilize these principles, the quantum field theory, the fractal geometry, the gravitational effects, and to unify all those theories. And then we're making the experimental predictions, and now we're in the validation stage. We're looking for partners, collaborators, institutions, universities, different types of folks that are working in areas like this, that are interested in collaboration on some of these, because there's so much that we're discovering and finding out every day that it's almost overwhelming how many things that we're looking at working on. So I'm hopeful that someone will see this and go, hey, this is neat. So how we're reducing, or how we're transforming different industries, the big thing here is we want to do the carbon emissions reduced and the renewable energy adoption. Those two things just in general are going to be, that's kind of the major purpose of why we're doing what we're doing here. So this is kind of the plan for the entire project plan and milestone. And this is really focusing more on the hydrogen splitting semiconductors, not so much the spark plugs. The spark plugs goes along with this, but they are actually quite different processes. So we've done some initial screenings of the materials where I'm focusing, on silicon because of its abundance, obviously, and it's very cheap. However, there are some really neat materials like graphene and C16 that are very promising as well. So we're not, shutting out any of those other things as well too. But for scalability, really looking at common available materials. We're working on the optimization for the synthesis of this right now. Expecting by the end of the year to characterize the different optical properties of everything. Into next year, we're going to integrate the materials in, and then hopefully by 2016 or 2026, we'll be working on building the final real prototypes. The budget for this, really, I put this in here just to show the value of people. While this is very heavily AI driven, and there's very advanced AIs that's working on this, the research personnel is what's important. The domain knowledge, the understanding of what needs to happen, the strategy, all of those other types of things, AI can't do that. So this is really what's important, and that I don't see changing really ever. The material selection, again, these are some of the property. We were looking for efficiency and sustainability. I had kind of gone into that a little bit earlier. How we go about selecting it too is we want to, the nano structuring part of it is we go in and optimize the band gaps. We look for the defect pacifization to kind of understand what defects can stay and what can't. And then really ultimately, improving both the chemical and thermal stability of that particular substrate. So this is where we're at right now. We're at the material synthesis stage and trying to kind of figure out all of those different pieces. The material characterization is next, fabrication, and then we're going to get into testing. Partnership developed. These are different companies that have expressed some interest or are watching us per se to see, if this is real, if it's going to take off, and we're hopeful. Especially Ford, and there's a couple on here that aren't that are actually big players that I didn't put on here, but FedEx, UPS, and DHL are all interested in the hydrogen splitting spark plugs for their fleets. So once we get this done, we have some very big players who are interested in coming on board. The expected outcome of this is we're looking, we're going to improve the efficiency of solar energy into hydrogen fuel. We're going to have the stability be better. The semiconductors are going to be more durable. We're going to be able to engineer plastics. This is, or not plastics, or it could be a number of different substrates. But this is the thing about that when I say that that's interesting about this particular equation. By understanding the insights that it gives us, it enables us to regulate the uncertainty principle. In doing so, it also gives us the ability to alter and change some properties, meaning like, say, magnetism or some other different types of things. We can now engineer at a quantum level new materials. And that, I think, is something on the material science side that's going to be quite groundbreaking. I don't even know where that stops. So, and then we also want to make sure, again, that we're scaling this production, meaning we're going to need good materials that are highly available, and we're looking, potentially at plants in Asia, plants in North America, a plant on each continent, basically, so that we can get distribution going in that direction. So these are some other applications of hydrogen splitting besides cars and besides spark plugs. Hydrogen fuel production, that's the big one. We can start to do this really on an industrial scale. There are, not to paint a rosy picture, but storage is an issue. There are some issues, but we will get through those. We have some very, very intelligent people working on this. Ammonia synthesis, this is a big one. Think about ammonia. And what we would need to do as far as putting the hydrogen synthesis into it for, and even methane, those other types of things. There's so many chemicals that use hydrogen in ways that they can now be completely renewable and much more sustainable. Oil refinery, again, that's another one. Hydrogens, we use that to process heavy oils. Metal processing, purification of like steel and titanium, food processing, glass production. This is the one I'm working on right now, the semiconductor fabrication. And renewable energy storage. This is a prototype or an image of what a fuel cell, a hydrogen fuel cell, could look like. Again, we're really kind of trying to push the envelope here and build some things that haven't been done before. Clean transportation, that's something that we're going at. This is kind of the idea of the fuel stack. That would have been a cell inside the fuel stack. Here's a hydrogen filling station, where they would go in the vehicles. We've kind of done a lot of it. Decarbonization, cement production. I mean, that's another way. Glass production by producing heat. So we can replace natural gas. We can replace fossil fuels. There's a lot of different things that we can do over time. This is going to take time, but we have a pathway now to a clean, renewable source of energy that is scalable and efficient. Hydrogen heating and cooling, there's going to be more and more advances. We're going to have room temperature quantum computers. We don't know how yet, but it's going to happen. We have the technology and the means to do this now. It's just a matter of actually having people do it. Space heating, water heating, backup power, all kinds of ways that the hydrogen can be used. This is an important one, and that's why I keep focusing on ammonia and methane. But if we look at the percentage of ammonia from green hydrogen today, and then the percentage of ammonia from green hydrogen by 2030, this is a big jump. And this is something, this is hopefully that we want to see. But this is what's even more important, is the decrease in greenhouse gas emissions. And think about that, it's from our fertilizers and from our food and those other types of things. It has a major impact on the planet, often overlooked. And so we're hoping to increase the percentage of farms using the green hydrogen fertilizer by in the next 5 to 10 years. It is a feed production, methanol synthesis, and then for the oil, crude oil, biomass, those areas for hydrogen too, it can be used for refining petrochemicals and biofuels. Energy storage in remote areas is one thing we want to take a look at. I'm hopeful by the end of 2026 we'll be able to put a electrolyzer system in an Alaskan village. And then by this time, we'll see if it gets a 50% reduction and then scan those out. But the goal will be to have, maybe 100 or more electrolyzers in very remote areas for power, by 2035 or so. These are some of the companies that we'll be working with in doing that. Marine transportation, this is another one where we can switch all of our marines and boats over to the hydrogen fuel cells. So this is where we're at. We want to install the fuel cells and storage tanks on ships and ferries. We're going to use the electricity from the fuel cells to power electric motors. The fuel cells then provide onboard appliances and navigation systems. And then the excess electricity, once we get to that point, can actually be used to produce green hydrogen. And then the green hydrogen can be stored. So all of those things will go into play. There are, major maritime companies that can benefit from this. The U.S. Navy, many navies around the world would all benefit from this as well. This is what we're wanting to look for too. This is kind of the share of how hydrogen is being used, or how it's. We've got electrolysis right now: coal, natural gas, and fossil fuels, and we're trying to improve that over time. And basically, and to conclude, this is an example of the quantum coherent tunneling pathways. And so this is where we would be using the MOQ to determine MEQ to determine some of those things. This is another one of the algorithms as well. So this has been a lot, I believe, that I've kind of put out here, and it's very exciting. I'm hopeful that we're going to be able to continue to do this and bring on even more players with more funding and smarter people. Done one way or the other, because if this is accomplished, it will greatly benefit all people all around the world, anybody who needs transportation, and will also help us really reverse in some ways. If we're pumping oxygen out of the back of our vehicles, that can change things for us. So that's all I have today. I can stop now. Are there any questions?